Okay, good morning. I hope you can all hear me. Okay. It's okay. Yeah, good. So, as Neelima announced, it is recurrence networks and dynamics from data. This is slightly different from the dynamics that we have so far heard and the construction of networks that we have so far heard in this program. In that, I am now constructing, when the program is also climate dynamics and networks, so we are trying to see what is the nature of the dynamics underlying the data produced in a climate system. Basically, that's what we were doing. So let me thank Neelima and Ram for this opportunity to present this topic. This is one of our recent works. So I will start with a very brief introduction. Then I will talk about how I have taken the data from the different climate zones of the country, reconstructing the dynamics from this data. Then we look at patterns of recurrences in the dynamics and we try to quantify those using some measures. I will be touching upon mainly what we call as recurrence networks and their measures. So using this, I am trying to group these locations into clusters based on how these measures vary over time. So this will also help us to look at some of the transitions that can happen in the dynamics over time, some shifts in the dynamics, etc. And more importantly, I am concentrating on the spatial and temporal heterogeneity across the country. And then I will try to connect with some of the major climate events towards the end. So most of the global challenges we have to understand from data of complex systems. Some of them I am showing there, but we are going to concentrate on global warming and other climate-related challenges, global challenges, and climate being a totally data-driven science. So we have to concentrate on data. We should be able to analyze data, understand data. That is very important. So how do we understand data from complex systems? This is important for characterizing natural or all the underlying dynamical processes in complex systems. Why do we even worry about a dynamics underlying a data? So the argument is data varies in a non-trivial manner, which means there is an underlying dynamical process which produces those changes in the data. So we should be able to capture that dynamics from the data. Then we can see how this data, how highly irregular it is. Most of the time the data is irregular, which means we expect the dynamics underlying the data also to be very complex and irregular. So how do we understand that? That's what we are trying to see. And coming to climate systems, this is a complex systems approach for climate data analysis. And climate data, as we have already seen, exhibits so many complex variability features. And there are major issues like non-stationarity, multiple regimes, tipping, nonlinearity, and complex relationship. And there are internal dynamics as well as external forcings. People say even urbanization, industrialization, everything affects the climate of a location. All these things are there which are external to the dynamics. Internal dynamics itself is very complex, involving large number of variables and parameters. So all these things are there when you look at climate system as a complex system. Now what we do is we try to look at, do a nonlinear time series analysis for this data. So we have a sequence of observations that can capture the dynamics, and we follow a dynamical systems approach where the nonlinear and complex nature of the underlying dynamics and its transitions can be characterized. As I said, we will look for spatio-temporal variability in the climate dynamics by doing that. Now coming to the Indian climate over the country, India, we know that there are a lot of heterogeneity in the climatic conditions over different parts of the country. We know in India, we are very, very diverse regarding culture and food habits, everything. Climate also is equally diverse over the country, if not more, starting from Ladakh in the mountainous area down to coastal places like Cochin and Pondicherry. And then we have desert regions, we have the Northeast. All sorts of diversity are there. This is there in the climate also. So it's a little bit of heterogeneity and diversity comes from the geographical locations. But there are other influences like atmosphere, ocean, land, etc., which makes it very complex. So this heterogeneous nature can come from spatial changes in atmospheric dynamics, wind circulations, moisture, and also human interventions like urbanization, industrialization, etc. For example, metro city can be very different from another location. So in this dynamical systems approach to study data, we look at long-term meteorological time series from different locations, compare their underlying dynamical nature and their variations, so that we can look at the spatio-temporal variability and we can identify locations that show the similar variability in the dynamics over time. So this will help us to understand the complexity as well as the climatic conditions. So this is how I have taken the data from different parts of the country. Now, this is a classification, Kuiper-Geiger classification or KG classification that is usually done for climate zones. And in India, based on this classification, there are 6 classifications there. The climate's various zones, as you can see, it varies. There are 6 zones in this country itself. And we have picked some locations, 15 locations from the different climate zones of the country. These 15 locations are chosen from the different climate zones, and I'm grouping them now, showing how many are from the same climate zone, etc., like this. And then these notations also will be useful later. So these are the 15 locations that I have chosen for the study. And these data sets are the reanalysis data sets of temperature and relative humidity from this NCEP site. And we are considering the period from 1948 to 2022. Which means 75 years of data from 15 locations. This is my starting data set. And I'm just showing you to get a feeling for the data. I'm just showing you the temperature data. For example, this place, Bengaluru, this is how it is. These are all temperature data. And then from some relative humidity data also I'm showing you just to get a feeling for it. But now we have to do a pre-processing of this data. So there are different techniques of pre-processing. Specifically in this particular case, for my purposes, I am using it in one particular way. That is, first I am binning it for such that I have only 2 points per day. So as you know, binning a data set to some extent reduces noise in the data. And that gives you the less number of points, but that is good enough. And then there will be an annual periodicity because we are dealing with climate. So periodicity will be there, very strong, an annual periodicity. That is removed. Then there can be other fluctuations and seasonal components, which I remove by running a moving mean window with a mean of window size of 30. And then this is finally rescaled to the range 0 to 1, so that all of them, the values all lie in the same range. That is inconvenient for us. So these are the data sets after processing, after pre-processing, Bangalore, Delhi, Ladakh, Manali, Pondicherry. To give you a feeling, this was the data, original data of Bangalore before processing. And this is the data after processing. So that's what I have done. And then this is relative humidity from Pondicherry, climate, etc. For example, here, this Pondicherry, this was the data initially, and this is after the processing. So we have now made everything into 0 to 1 range. Similarly, for Ladakh, this is relative humidity for Ladakh, and then this is before processing. Sorry, this is after processing. So just to give a feeling for that data. Now, what we want to do is, from the pre-processed data, we want to construct the dynamics underlying the data. So as we said, there are several dynamical processes happening, but we have a method of recreating the dynamics, and then we can look at the pattern of the recurrences in the data, in the underlying dynamics that we get, and then compare. So when I say we are recreating the dynamics, we are constructing a phase space of a properly chosen dimension. And then in that phase space, you are actually looking at the trajectories of the dynamics. And then we will look at the recurrence pattern in the data and then try to classify them so we can know whether transitions are going to happen. And in general, I'm not doing it now, but we can say in future, there is a prospect that you can make predictions and even we can model the dynamics if possible. That is too much at this stage, but we can say that's possible. So now coming to how do we reconstruct the dynamics. So this is a standard procedure that is used in nonlinear time series analysis. This is called the Reuel-Takens embedding. So we are starting with a scalar time series, and then we construct the space of dimension m by just splitting this data into points with a delay time, properly chosen delay time, which we call as tau. So we have a set of values like this. I indicates the time index or the index of the data, and then we are separating them with a delay time tau. So if in an m-dimensional space, we can say at a given time t, if the point in the trajectory at time t is represented by a point in an m-dimensional space, its first component is this, next component is this, like that, and the mth component is this. So you have an m-dimensional vector created from that. But only problem is, for any given data set, you should be able to assess what is the proper tau to be chosen as well as proper dimension m to be chosen. So tau, normally the standard procedure is to calculate the correlation as a function of delay time, and we find out the value of tau at which it falls to 1 by e. And then we will use that. And m is also calculated from a method There are several methods. In my next tutorial, I will tell you a few more other methods that are used. But now I am concentrating on one particular method, which is called the false nearest neighbors method. So this is a recent review that we have written. All these details are given in that. Now coming to the choice of delay. So as I said, you define autocorrelation as a function of tau like this, which means for tau equal to 0, it should be 1. And if you increase tau, the correlation decreases. And then at some point, it becomes 1 by E of the starting value. That value of tau is, you say, is the proper delay time to be used. And then false nearest neighbors, of course, these I can...
which value of tau did you say?
This value, this is an example I am showing. So where the value for comes to 1 by E of the starting value. So correlation decays as you go away in time. So ith point, I plus 1, I plus 2, like that you are moving.
See, many people use the mutual information.
Yeah, mutual information. I didn't show all the methods. Mutual information is also one method where you choose the first minimum of the mutual information for tau. That's also possible. That's another method. And in this talk, I thought I'll mention only one method like that. Later we can increase it. So this is a method of false nearest neighbors. Concept is very easy to understand. For example, if you have a three-dimensional trajectory, you are projecting it into 2 dimensions. You know that there will be some points which come close together, which in the 3 dimension would have been resolved along the Z direction, let's say. So if you look at the neighbors of the trajectory in the M dimension and in the M plus 1 dimension, if they move apart, that means neighbors are actually false in the M dimension. So if you have the correct dimension, then the false neighbors will go to 0. So thereafter, for any higher dimension, they will be 0 because no further resolution is required. So we want to find out the minimum dimension to embed this trajectory such that that gives you the required dimension. That's the method. So equations and all we will explain later. It's understandable, but let us explain that later. And just showing that this is a Rosler time series. And how do you actually pick up this? So Rosler has a delay of 13 time steps. So you take one value here as the first component. The next one is here. Next one is here with delay tau like that for 13 steps. And then you get all the points. Here it is in 3 dimensions. So 3 points which will give you this in this. This is a 2-dimensional projection of that. Then you go to the next one, find out its other components, mark it. Go on doing that. And when you have done it for the full time series, you get the reconstructed trajectory. So that's the general method. I'm just indicating that. Now, once you have got the trajectory in the proper phase space, then you look for the recurrences in the trajectory. So our general concept is that all bounded systems will have to recur. If they are exactly periodic, they recur at the same point after the periodicity tau, t. But if they are not periodic also, because it's a bounded system, the trajectory is going to visit the same region of the phase space again and again. So we want to check how many of them are recurring within an epsilon neighborhood. They may not exactly repeat because they are not always strictly periodic, but they will recur up to some region. So if it does that, then we say there is a pattern in these recurrences, which is inherent to the system, inherent to the trajectory, therefore characteristic of the data. So how does that pattern of recurrences happen? How do you capture it using some measures? So one way of doing it is to make a recurrence plot. Then from that, you can construct a recurrence network. And as we saw in the previous lecture, there are some quantifiers or measures of a complex network, which we will be using. And this is efficient and powerful because this is useful for non-stationary data and very short data sets also. Because normally there are other methods like multifractal measures and so many correlation dimensions. Those require large data sets. To the extent that for multifractal analysis, if you require 30,000 points for one data set, here we can manage even with 1,000. So we get reliable and robust measures. And also it can give you information about the transitions as well as the changes in its complexity. Now coming to the method. So a recurrence plot is the one that today I'm not going to recurrence plot measures, but I'll just show, you can even skip this. We can directly go to networks, but I'll just indicate how do we define recurrences. So it is at return of the state of the system to an earlier state within epsilon. So we can actually construct a matrix like this, Rij matrix, depending upon if the distance between xi and xj, this distance can be pure Euclidean distance in that m-dimensional space. And then if that distance is less than an epsilon, we say this Rij is 1, otherwise it is 0. So basically you get a matrix of ones and zeros, a binary set of numbers. And then we can plot it as a two-dimensional plot, then you get the recurrence plot. Or from the recurrence network, you can go to recurrence. This Potsdam group has done lots of work on that. All these algorithms that are used are also available in the Potsdam site for free. There are very good tutorials also available. I can give you the link also for this. This is the package, PyUnicorn package that is put up in the Potsdam site, PIX Potsdam. Now here again, the choice of epsilon is very crucial. We will come to that. Now, how do we construct a network from the trajectory? So we assume every point on the trajectory as the node of a network. And if the distance between the ith node and the jth node is less than some epsilon, then you say there is a link. We put a link between I and j. Otherwise, it is not there. So basically, you have to calculate the distance between every pair of nodes, again as the Euclidean distance like this. And then then Aij, the element of the adjacency matrix Aij is 1 if it is less than or equal to epsilon. If it is greater than that, it is 0. So basically, this adjacency matrix is the one which will give you every information required about the corresponding network. So I is equal to 0 because we don't want self connections or self loops to be made. Therefore, we can actually get the Aij can be derived from the recurrence matrix also, which we have defined earlier. Normally, computationally, that is what we do. So just remove the self connections, the delta ii here, sorry. And then you get Aij. That is the matrix. So I'm showing it pictorially here. This is the time series that you have originally. This is the reconstructed phase space from this time series or data. So this is a two-dimensional projection, xt and xt plus tau. If you look at that, for example, if you want to see how to connect this node y2 to how many nodes you want to connect. So take an epsilon distance here, whatever you define as your epsilon. Within that distance, how many points are there, you connect all of them. Again, do like that, and then you finally get a network structure like this. So this is simple. You can do it like that. But the choice of epsilon. And here also, there are several methods to choose this epsilon. I'm not going into details. Some details are already here in this paper. You can check it. Otherwise, we'll discuss it in the next tutorial. But basically, the idea is, if your epsilon is very small, it can happen that it is not forming. All your points are not forming a single network. There can be isolated clusters like this because your epsilon is very small. You should increase the epsilon, then more and more connections will happen. So at some stage, it becomes optimum and you get all the points connected. But if you overdo it, again increase it, it becomes sort of a random matrix, random network, because this will mask the actual structure of the underlying network. So you should have an optimum choice for epsilon. There are different ways of getting it. There is a connectivity measure based on the Laplacian that you can derive from the adjacency matrix. There are other methods of doing it. So people do it in different ways. I will explain how I have done it in this particular case, but one can actually do it. So from this is actually for the Lorentz time series, and you can see how you had to choose, or as you increase epsilon, what happens to the network patterns. Now, once you get the recurrence network, we can use some of the normal measures of the network. One thing, of course, is the degree of a node. So the advantage is once you have this, everything can be calculated from the given adjacency matrix. So this will give you the degree of the ith node, and this will give you the link density, which means the average value of the link of the present number of links there. So the total number of links in the network divided by the total number of possible links in the network. So that will give you the link density. And then what is known as the characteristic path length is, between I and j, you look at the shortest path. So it's possible that I is directly connected to j. Then the length is only one link. But it's possible that it is going like this. I is here, j is here, it is going like this. So the shortest distance is this. It can have many other connections to go from I to j, but we only look at the shortest distance. Go on doing it for every pair of nodes in the network, and then take the average. That gives you the characteristic path length. This clustering coefficient is another one which I am not using in today's talk, so let me skip that. Now coming to what I have done for the climate data. So delay time, tau, as I said, I have taken it as the value where it falls to 1 by e. Now, the m value that I have, because I have to compare large number of data sets. So the m value that I have chosen as the maximum among them. The reason being that, as we said, once you reach the correct dimension, any higher dimension doesn't matter because all your measures are going to saturate after that, whatever measures you calculate. So it doesn't matter if for one data set it is 4, another it is 5. For this also you can take 5. Doesn't matter because all the measures have already saturated above that. So for compare the data sets, I am taking m is equal to 5. That is the highest m that you get, that I get for the present data sets. And then this threshold epsilon. So that also, as I said, there are different ways of doing it. In this particular case, what I have done is, I can calculate the pairwise distribution or pairwise distances in the m-dimensional space. That means in the 5-dimensional space for each data set and look at their distribution. And I take the 5th percentile of that as the corresponding epsilon to be chosen. This is one way of doing. People use 5th or 8th percentile. You can just try with that. Epsilon is also taken in too many other different ways, which we will discuss later. And this average is taken for all of this 5th percentile for each data. We take the average over that and use that as your epsilon for all the data sets. Now, in this particular work in the climate dynamics, I am interested in the transitions. Yes. The dimension, embedding dimension. So if you have the data sets, as I said, we have to embed it in a higher dimensional phase space because it actually comes from a higher dimensional system, even though you have only one data set. For example, temperature.
I will become expert, so you can spend a little bit of time even on the board.
How to? Can we do it in the tutorial? We can do it in the tutorial or now itself?
Whatever.
Yeah. So what I mean is, we have to embed it in a higher dimensional space, that we know, but how do you choose that dimension? That's what we are saying. So earlier we said, no, we have to do it in one method is false nearest neighbors. So if you are using a lower dimension than the one actually required for the system. See the system, for example, Rosler system, Lorentz system is 3-dimensional system. Suppose you try to embed the time series of Rosler system in 2D. Because it's like projecting a 3D system into a 2D, because of which there will be so many points which come close together, which in the original 3D, they may not be close. So you look at points which are neighbors in 2D, go to 3D, again look at the same points, the distance between them. If the distance is increasing, then you say they are actually false neighbors, they are not correct neighbors. If they are correct neighbors in a higher dimension, the distance will not increase too much. That's the point. So this way we will be able to do it, and I have taken m to be 5 in this case, as I said, because there are so many different values for m you get when you have a large number of data sets. For each one, mostly I was getting 4 and 5 for almost all of them. So higher dimension doesn't matter, but if a 5-dimensional system is embedded in 4 dimension, it's a problem. But 4 dimension can be embedded in 5 because we are not actually looking at the trajectory, but measures from the trajectory, which will not change. That's why we are choosing m to be 5 in these cases. Is that okay? Okay, so then threshold also we said, how do we choose, etc. Now, because now we are looking at some transitions that must have happened in the climate dynamics over time. We have the data from 1948 to 2022. Over that time, so we heard about global warming, everything shifts in the climate dynamics around 1970, things like that. So I'm just thinking, can we do a sliding window analysis to capture these changes over time? So sliding window means I have actually something like more than 54,000 data points after that binning everything done. I divide them into one window of 500 steps. That means approximately 7 years. Then slide it by 5,000 steps and slide it by 500. So it's a set of overlapping windows. That's why we say sliding. It's not like segmenting the data. We are not segmenting. We have first 5,000 points. Slide it by 500. That will be 500 to 5,500 next window. Then again slide it. So this will be 1,000 to 6,000 as your next window. Like that you go on doing. So that any change that happens in the underlying dynamics over that period can be seen as changes in the measures that we are calculating. So that's what I am doing. So then we embed each data within each window and get the corresponding attractor, compute the measures. Mainly I am concentrating on link density and characteristic path length from the recurrence network of the embedded data. So basically now we are getting in a way another time series, but this is the time series of the measures that we have calculated. LD as a function of time for one data itself, CPL as a function of time for one data, like that we are getting. So their variations over time then can indicate changes in the underlying dynamics. That's what we want to check. So just to give you some feeling for the reconstructed trajectory at different timings, this is the temperature data from Delhi. You see, 1957, this was the trajectory, 1968. I think if you look at it carefully, you can see some differences. Do you see differences in the trajectory? This is a two-dimensional projection of the five-dimensional phase space that I have created. Here actually color has some meaning because dark brown to light yellow indicates time direction. So the darker ones are the starting values and then it is moving around. So even though the shape may look the same, the timings may not be the same in the exact same trajectories. So there is a difference in the structure of the phase space trajectory that has happened over time. This is around 1957, this is around 1968 at the middle of the window. Yeah. Yes. Each window I am embedding. That is that 5,000 points. And then calculating the measures from that. Then slide it, again calculate. So, and when I plot that measure against time, the time corresponding to the middle of the window is marked. Measure is marked around the middle of that time. So that's what I am showing here also. Around that time, 1957, if you have 5,000 points. Yeah, because we have to compare. So we have taken the maximum dimension I got as that same dimension for all of them. That's how we are doing. So this is for two timings in Delhi. Now this is for the relative humidity data of Pondicherry. So this is around 1961, there is 1978. This is just to motivate you that there is some meaning in studying this because there are fundamental changes that happen to the dynamics over time, which is reflecting the changes or dynamical processes that affect the climate of the location also. Now coming to Bangalore, the same place, you see 2017, 2008, 1980, 1975, different timings. So the structure is also slightly different, you can see. And this difference in the structure, we will be able to capture using this recurrence network or other measures in the recurrence network. That's what we are trying to do. Now this is the network. See the network of Bangalore. Again, the same, I have shown the same date here, 2017, 2008, 1980, 1975. So when you come to, some issue here. I mean, you can make out the network, no. So it was not that thick in it was looking like this only. I don't know what happened. Anyway, here also the shade color code has some meaning. Higher degree has darker shade. So you see, higher degree nodes, how many are there, how are they distributed, all these things are differing across these different networks that you are creating. The pattern in which you draw the network is, of course, you have some say there. You use the Gephi software and you can adjust. Vedartha knows that, how we can do that. Doesn't make sense. I mean, it doesn't carry any information why you make it circular or things like that. What matters is the nodes and their links. So degree.
Why the network actually leads to both?
No, they don't correspond to physical points. No, they correspond to some time. Yeah,
right.
Correct.
So there are some points at which, there are some times at which you actually get
higher
more
degree.
higher linkages
Higher
than
degree.
at other times.
Correct. That's what is happening. And how do we capture it and measure it? That's what we are saying. So this is again temperature data from the place called Manali. 2015, the trajectory and the corresponding network. 1971 trajectory and this network. This is for temperature data for Pondicherry. Again, so 1959, 1975. So wherever a lot of changes are there, I'm just showing it so that you understand like that. And this is the temperature data for Ladakh. This is 2000 and this is 1969. So you see, there is definite change in the structure. Even if you can't make out in the actual trajectory that is shown here, you can actually make out that from the network that is shown. Now, how do we plot?
The lower thing is the projected trajectory.
Which one?
The pink stuff. What is that? That's
This
the
is a
projection of the trajectory from the 5D space
This
to
is
the 2D.
This is the projection of the trajectory in 2D,
to a 2D
space. Xt and xt plus tau. So xt plus 2 tau, 3 tau, 4 tau. Those are the other dimensions. Because we don't go to that, just to indicate that we are showing only two-dimensional projections. But this is the corresponding. The network is constructed from the 5-dimensional space by looking at distances in the 5D space. That is what we have done. So these are the projections, network we get. Now, another way of showing this, because definitely there are variations for these measures over time. There are variations with respect to locations also. So together, these two together, we can actually show it as a heat map here. This is for link density from the temperature data. So we are showing all the locations here, starting from, the order is chosen in such a way that those showing similar variations come together, but that doesn't, we will show you, quantify that later. So this is time, and this is the color code, which indicates the range of values that you get for the link density. This is the heat map for the characteristic path length. Again, the same location-wise and year-wise we are showing. This is heat map for link density from the relative humidity data. Again, the range is shown here. And then the heat map for the characteristic path length or CPL over time with respect to the different locations. You will see the order of the locations are changing. When you come to relative humidity and temperature, there are differences. There is a lot of heterogeneity that is there. Now we will see how to quantify this or how to explain this because we know that there are changes over time for the same location, and there are changes over the locations also. So do they make sense to us in any way? How do we understand the underlying dynamics from it? So we know that link density high and path length low means the dynamics is more regular. Dynamics, okay. So if the CPL is high and link density low, that means it is more complex and irregular dynamics. So link density and the other is characteristic path length. So these measures, so this is roughly we can say, because the system is anyway non-linear, we have verified this using multifractal analysis earlier, which I am not showing here. So we know that there are some non-linear processes involved, large number of them which produce this data. So then the dynamics is, but in time, it is passing from a more regular state to a more irregular state. We can't say periodicity to chaos, etc., because I feel in the regular phase itself, it is chaotic. But due to some influences, it can go, some external influences, some stochastic nature can come in, then it becomes little more irregular. So
you can actually quantify, no?
Yeah.
Whether it is more or less.
Yeah, that I'm coming to. Now, that means increasing trends in CPL values means shift to regular dynamics. Decreasing trends in LD link density means more irregular dynamics. So these variations will tell us about what are the type of changes that happen to the underlying dynamics. Now, what we did is, before I show that, I will see that we actually clustered the locations based on these variations. That means locations which have the similar variations. The values need not be the same, but the variations or the changes occur at the same time. Like that, over time, if they are undergoing these changes in a similar way, then we say they form a single cluster. So all such locations will form a same cluster. For that, we did a Spearman cross correlation matrix or for all these 15 locations pairwise, then hierarchical clustering, so that it will group locations which are very similar to each other with respect to these variations. And we find we can cluster all these 15 locations into five clusters based on temperature data and relative humidity data, and they are not the same. Temperature data gives one set of clusters, relative humidity gives another set of clusters. Now, I am just showing these variations, actual values of these variations and values and their variations with respect to those clusters. You can see in the same cluster, the stations that come in the same cluster, they are shown here. So they have similar variations in CPL and LD that you can see. Similarly, these two, see, the variations are very similar with respect to time. These also. So even though values are not the same, variations are almost the same like that. This is for temperature data. Yes. No. So, no. They are the same. For example, even though slight variations are there, we show the variations mostly based on LD, and they are almost the same with CPL also. You can see that. The CPL variations, the LD variations. See, these two go together, no? It's the same cluster. We are using both LD and CPL for the clustering. Okay. Actually, the clustering was done with LD, and we find CPL also follows it. That's it. Yes. We find that CPL also follows it. In fact, we have done DET and laminarity also. There also it is the same. So this is for temperature data. Then we come to relative humidity data. Here also you see same variations for these three together. So they form one cluster. See, Tawang is a location which is very different with respect to relative humidity. They don't follow any other station. So it's a singleton. Then these are the stations, and these coastal stations, all of them follow almost the same. As you can see, the values are not the same, but variations are the same over time. So we say that they form a cluster like that. Now I am marking these clusters in the map of India. I hope you remember the earlier map which I showed with respect to the climate zones and the 15 locations I have chosen. Now these 15 locations are then now clustered based on the temperature data, variations in the recurrence network measures from temperature data, which I would say that the variations in the underlying dynamics at these stations, and I am grouping them. Those shown in red are the ones which don't follow the earlier KG's climate zone classification. They are different because the climate zone classification, as most of you know, is based on the mean temperature and what else do they say, changes in that mean temperature and things like that. But here we are looking at the dynamics. So in two locations, even though the variations in the temperature can happen in one way, their underlying dynamics can be different. That's what we find. So just to compare, I am showing you the original climate zone classification also. These are the, yes. Yeah, color code is the climate zone. My points are shown in the same color if they form in the same cluster. So there's a color code for the cluster. These small circles have one color. That is my cluster color. And this big shading is shown over the map. This is the climate zone.
Clustering, what is the color coding?
See, this is forming one color. These two form another color. No, just identifying by different colors.
Just identifying.
There is no color coding here. For example, those stations which are together here, they are shown in the same. This Tawang, Manali, and Ladakh. One color. Values. Variations in the values. No. Okay. Similar variations in the values. Geography, I am not worried at all. I'm little worried about the earlier climate zone classification. That is shown in the background color and the written here, which zone they belong to, etc. But here you see the Ladakh, Manali, and Tawang. They are in one group. But original classification, Ladakh is different from Manali and Tawang. But my classification, it is slightly different. Similarly, Shimla, Delhi, they form one group. Cluster 2, but here Delhi goes with Bhopal and Shimla goes with Tawang and Manali in the climate zone classification. But somehow I find there
depends on the time of the year also.
No, it's over time.
Over time.
This is the variation, similar variations over time from 48 to 2022. That's what we are showing. So here, but I have a feeling all these cases are little bit borderline if you can see that climate zone coloring. Maybe that's also one reason, but we will see what other reasons can be there. So similarly, these red ones are the ones which are out of correlation with the climate zone classification. But Bhopal is also border, Delhi is also border. But Delhi, Bhopal and Mumbai. But they can have other influences possible other than being coastal. Mumbai being a metro city is influenced by so many other factors. That also may be the reason. Something like that we can say. Now we come
here. I think averaging is actually missing things. But anyway,
averaging
is actually missing things. But we'll talk later.
Okay. Yeah. Because I was concentrating on how the climate dynamics changes over time. If they change in the same way, they have to be classified into one group.
But I think you have to choose the time scale in a very careful. We'll talk later.
Okay. So now this is based on the relative humidity data. Again, we say here also we can cluster them, but this clustering again, some of them remain the same as the earlier cluster. As you can see, this group is the same for temperature and relative humidity. I am showing again the temperature classification. This is the relative humidity classification. For example, these 5, in a way, except Bangalore, those are coastal ones. They follow the same. But here again, this is Ladakh, Manali and Tawang here, but Tawang is a singleton here and Ladakh and Manali goes with Simla there, like that. So some variations are there, but otherwise they follow this is again the climate classification, climate zone classification. So these are the climate zones. This is from temperature data. This is from relative humidity data. That's what we are seeing. Now let us see what more can we understand from this. So there is, first thing to notice is there is lot of spatial and temporal variability. I'll finish. From recurrence patterns, we find there are variations and these 15 locations are grouped into 5. So clusters are not the same for temperature and relative humidity data. That is one thing you notice. And clusters do not exactly follow the Köppen-Geiger classification. So the present classification is based on the recurrence pattern in the dynamics underlying the data rather than statistical features or average values. So we don't expect them to follow this KG classification at all. But let us see. Now this is another way of characterizing. This is called a scatter plot, indicating times of occurrence of maximum for blue and minimum for red. So if you take the average of all these values of all the values of one data set for all these windows together, and then you take the standard deviation sigma, wherever it crosses sigma, we say that there is a change happening. If it is decreasing, we give it a red color, and if it is increasing above sigma, we give it a blue color, so that we can understand the durations during which they were high or low compared to the mean value or near the mean value. So this indicates the transitions that can happen. This is from temperature data. This is LD related link density measures, and this is for CPL measures. So this in a way can tell us how changes start and then how do they go about and how long it was remaining low or remaining high, etc. Now from this, how do we understand the shifts that can happen? So from the earlier scatter plot, we see that there is a decrease in LD or an increase in CPL around this time, 75 to 85, with a few locations changing even before that, 60 to 70. So this we think can be linked with the strong El Nino and La Nina that alternated during this time. With they have opposing influences. As you know, El Nino and La Nina, two opposing phases of ENSO. And if they occur one after the other and both of them are strong, then they have opposing influences on the dynamics because of temperature, rainfall, pressure, everything is changing. But because of that, the dynamics becomes more irregular and stochastic because of the rapid changes that happen one after the other. So this is our interpretation, but we find that this is also consistent with a climate shift reported around 76 to 77, with changes in the Indian summer monsoon, because ENSO is well known to modulate the summer monsoon also. Now, increases in the LD or decreases in CPL also were seen at a later stage beyond 1995 for most of the locations. That means the dynamics is reverting back to more regular nature. So if in that prime time, I find that this El Nino and La Nina are moderate and they are occurring intermittently with gaps. They are not continuously strong El Nino followed by strong and La Nina, not like that. There is intermittently changing and they are not very strong or they are moderate actually. So the system dynamics can go back to more regular nature. And also in mid-1990s, an opposing climate shift was also reported to that happened in 76-77, which had an influence on Indian monsoon onset. This also we can relate to our results that we find. Now, locations that show differences in the transitions are, we can say, is influenced by other geographical factors also. And this ENSO-ISM relationship also, people have shown, is different for North India, Central India, and South India like that. So that is also, explains the heterogeneity that you see in our calculations, similar to the heterogeneity that was reported between this ISM-ENSO relationship. This is again for relative humidity data. So in this case also we find there are times when they are all high values, then they go to lower values in showing there is a change in the dynamics and then go back to again regular dynamics. So this again we can say, but this is much more heterogeneous compared to the temperature data, location specific. And then around 1972, most of the locations are showing regular dynamics and irregular after 80. And few locations like what is it? This is Manali actually. Patna and Ranchi show irregular dynamics before 65 itself, but regular after 2000. Delhi is showing something very different, irregular around 85, regular after 2000. Tawang is also different. It shows irregular around this time and regular at this time. So relative humidity is affected, we can say, by extra factors, precipitation, moisture transport, sea surface temperature, etc. So that can explain this type of spatial variability. So now I am concluding. So we found that climate dynamics is affected by several climate factors that we know, and their impact on Indian summer monsoon and these ENSO oscillations are also known. So we know that climate dynamics is not uniform due to all these variations, and our studies also indicate that. So what we have done is we have reconstructed the climate dynamics using temperature data and relative humidity data from 15 locations from the different climate zones. Recurrence measures were computed from this, and we find there are transitions in dynamics which can be picked up using these variations. And based on similarity in the variations, we are classifying them into 5 clusters. But the times of occurrence and the significant variations differ from each location. So even within clusters in one location, the values are different, and the exact onset of changes also may slightly vary. So there are some heterogeneity, spatial heterogeneity there also. And these epochs of El Nino and La Nina, or the shifts in the pattern in ISM and other factors, have an impact on this, which explains how this heterogeneity happens, etc. So most of the things I discussed today have been published as a paper in Chaos. This is the pattern, this is the page of that. It's also a companion article published in SciLight as Dynamical Systems Approach to Studying Climate in India. So you can refer to that for more details. The student who worked with me on this work is Joshin John Binoy. He did it as his master's thesis with me in ISR Tirupati. Then he moved to IIT Chennai with Sujit's group. And now he is out of that place also and he's looking for a good PhD position. He's extremely trained in this type of work, very, very good trained. And then I have worked with Vedartha also earlier. He did his MS thesis with me long back in ISR Pune. Then he went to University of Potsdam for PhD, then University of Tübingen. Now he's back in ISR Pune as an assistant professor in data science. So while we were doing this, we have been discussing with Vedartha on several aspects of climate, and I gratefully acknowledge all that. These are my other collaborators who have worked with me in this type of analysis, but not with climate data, but with other types of data. Those are some of my references other than this. So let me skip all this. And thank you very much for your attention.
Questions?
Yeah.
So all your analysis is based on network measures, like so the link density and so on. So climate itself is physics. And can one get somehow a relationship between the network measures you are using and real physical phenomena? So that means we have of course all the climate models.
Yeah.
The data you measure.
Yeah, correct.
Because this is all.
That's right. Yeah.
Study. So where one can make this type of relationship.
See.
So to see.
Yeah. I understand.
Climate data are qualitative, so that.
I understand. Yeah, I understand. Correct. Yeah.
Is there any?
So I don't think so. Yeah. What I could say is when it is transiting from regular to irregular, more irregular nature, because of some added stochastic factors of things like that in the dynamics. And then such changes I was trying to correlate with other non-climatic shifts and climate changes, like ENSO oscillations, their influence or Indian summer monsoon influence, something like that. But other than that, as you said, see, actually this ISM study that I have shown is based on the pattern of wind circulation over India. So they are connecting it to some atmospheric dynamics and wind circulation. That they have done. But in my study, I don't think I can associate with any such dynamics because it is so complicated. You have to look at so many factors, so many variables and things like that. And you told me today that there is some modeling on climate. I would very much like to see that so that I can see whether say for example, can you write the climate dynamics in terms of a few variables as a dynamical system equations?
So of course, all the climate models do that.
Okay. So maybe I can look at some such model and see. Yeah.
So which is known, so to say, is put into climate models. Of course, climate models have different resolutions. So that means, so some of them have a rather high resolution, some of them not. So it depends also whether you have a regional climate model or you have a global one.
Okay.
And then not all the physics can be really, so to say, represented.
Correct.
But so the modeling is already at a very good stage.
Okay. Yeah.
So, but of
maybe
course, you have to look into the models, which type of equations they are using, and most of them really, when they include processes which are sub-grid scale, then they use parametrizations and the different climate models in the world. So there are, I think, something like 40, and use different parameterizations, and therefore they come up with different results. So therefore, if you compare different climate models, I would say you can compare trends, but you cannot compare
that's
values.
right. Correct. So trends is what I have also looked at in this, because actual values doesn't matter, only trends we were checking and trying to correlate those trends with other reported changes in climate. Basically, that's what we have done. But if there is a model, I would very much like to look at it, and I would like to know whether anything specific to Indian conditions are shown or not. You have to see. I don't know. What do you think, Vedarth? I think it's really complicated, no? Modeling.
Yeah, so
Modeling
what you are
part.
essentially saying is which is a good climate model.
Do you have one? Anybody has one? We can. Yeah, please. So I think this, when you say this reanalysis data, that is already taken care of there, no? So we didn't worry too much about gaps in the data. There is no gaps at all. They have doing. Reanalysis data takes care of all that. After measurement, they are taking care of all such issues. And therefore, but anyway, we binned it. We removed all these fluctuations and other things. And then we removed strong periodicities also. And then we say that what other uncertainty can be there, because these are actual measurements, and whenever there is a gap in the measurement or something, they are taking care of that. This is actually consolidated from so many observations, no? This reanalysis data. Yeah, and then yeah. Yeah. So in general, of course, if there are gaps in data, I have another set of slides for the next talk where I will show that there can be noisy influences which will affect the data, which we will not know. They may mimic like a dynamical system, but can be noise added to that, especially colored noise.
Saying noise, deviations from your method is making certain assumptions.
No, we are not assuming anything in the beginning, but we are looking at the pattern. This pattern also can be changing from a real thing because the system itself must be having colored noise. That is why it is changing, no?
But every method is built on certain assumptions. I'm just asking
correct, right.
how sensitive, let us say, misspecification.
Yeah.
Like
See, one thing is this presence of noise. The other thing is gaps. Suppose the data comes with gaps. Interpolation can add artifacts into that, which we don't want to do. So to some extent,
solid hypothesis testing framework.
okay.
Right?
Yeah. So one way what we do is with surrogate data analysis. That we normally do. So we either reshuffle it, we do it, no, for recurrence plot also, we shuffle it and then do it. That we do normally. I didn't show all the results, but we should do it. Yeah.
There are dependencies. Yeah, that's fine.
So you have that amplitude adjusted one from Fourier transform. That also we do. So then we compare the measures with the surrogates. Yeah. So that we do. So from that, the measures for surrogate and the actual data will differ with some amount when we say that, okay, this is not produced by noise. That we do normally. Yeah. Yeah. See, we actually binned it in such a way that you have 2 points per day. The actual data was more than that. Maybe it was, I don't remember exactly whether it was, I think it was 6-hourly data from the reanalysis. We binned it in such a way that we have only 2 points per data. So that to some extent, these small fluctuations will go away when you bin it. So we take the average of that many 6 hourly data for one day means it will be 8 sets. So you average it, or 4 of them average and replace it, again 4 average and replace it like that. And so have only 2 data per day then. Yeah. That's it.
Thank you.
Okay.
Then